Welcome to lesson 5.5. Today we're going to talk about Dalton's law of partial pressures. When gases are in a container, when you have different types of gases in a container, the pressure of the gases exerted in that container will be the sum of the partial pressures of each gas because they behave independently and the molecules do not interact with each other. So assuming that each gas behaves ideally, the partial pressures can then be rewritten as the ideal gas law. And then when you combine all that together, you end up with your sum of the number of moles of the various gases times RT over V, and that gives you the total pressure. This is a schematic of Dalton's law of partial pressure. So the gas represented by the blue in the container by itself. Notice there are two masses on top of it to keep that piston in place. The orange gas, notice there are 5 masses on top of it to keep the piston in place. So when you put those two gases together in the same container, if you total the number of masses, it's going to be this one plus that one. Gives you that masses. So that's how much pressure that's equilibrating between the pressure applied and the pressure the gas is pushing on. The pressure exerted by an ideal gas, it doesn't matter what the gas particles are, and so that means the volume of the particles themselves are not important because an oxygen molecule is much bigger than a hydrogen molecule. Forces among the particles must also not be important, so there's no interactions going on between them. So let's look at an example. We have helium and hydrogen in a scuba diving tank, and they do this mixture to help prevent a condition called the bends if people were to ascend too quickly. For a particular dive, 46 liters of helium at 25 degrees Celsius in 1 atmosphere and 12 liters of oxygen at 25 degrees Celsius in 1 atmosphere were pumped into a tank with a volume of 5 liters. Calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees Celsius. So we're going to take this 46 liters of helium and this 12 liters of oxygen, and we're going to put that in a 5-liter tank because gases are compressible. So where are we going? We're going to figure out what the partial pressure of each gas is, and then we're going to determine the total pressure in the tank at 25 degrees Celsius. This table indicates what we know. We know the initial pressure of the helium and the oxygen. We know the initial volume of each, and we know the initial temperature of each. We also know that we're putting it into a 5-liter tank, and it's going to be at 298 Kelvin. So what pressure are those gases going to exert in that tank? So what information do we need? We're going to use the ideal gas law. We know that the ideal gas constant, 0.08206. So how are we going to get there? First, we're going to figure out how many moles of each gas we have. And we do that by using the initial conditions. So 1 atmosphere, 46 liters, 298. That gives us our moles of helium. 1 atmosphere, 12 liters, 298. That gives us our moles of oxygen. So we know that we're putting those two gases into a tank. And when we put those two gases into that 5-liter tank, so we know we had 1.9 moles of helium. So we're going to use the ideal gas law again. We know these are the conditions of the tank that we're putting it into, 298 Kelvin and 5 liters. So that helium gas, that 1.9 moles of helium gas at that temperature and that volume are going to exert 9.3 atmospheres of pressure. Same thing we're going to do with the oxygen. These are the conditions we're putting it into. So we were able to calculate moles based on the initial conditions of oxygen. Now we're going to put it into a new set of conditions and calculate that we have 2.4 atmospheres of pressure. So the total pressure of the two gases in the tank is going to be an addition. So we're going to add those two, and we're going to get a total pressure in that 5-liter tank of 11.7 atmospheres. Another thing we can do with Dalton's law of partial pressures is something called mole fraction. Mole fraction is just the number of moles of the specific gas we're talking about divided by the total moles in the container. Again, we can use the ideal gas law and rearrange to solve for moles. And so when we do that, what that allows us to see is that mole fraction is the number of moles over the total number of moles, but it's also that gas's individual pressure divided by the total pressure by rearranging the ideal gas law. So this is how mole fraction can be defined. We can rearrange this equation to get that the pressure of an individual gas is equal to its mole fraction times the total pressure in the container. So that would give us the partial pressure of the gas. Partial pressure of oxygen was observed to be 156 torr in air with a total atmospheric pressure of 743 torr. So calculate the mole fraction of oxygen present. Going through the steps, what are we going to do? We're going to calculate the mole fraction. What do we know? We know that oxygen's partial pressure is 156 torr. The total pressure is 743. So we can get there by taking the pressure of the oxygen gas divided by the total pressure, and that gives us a mole fraction. Please note that the mole fraction, the number itself, is unitless because the units cancel out. Occasionally, when we're doing experimentation, we have to collect a gas based upon the displacement of water. And unfortunately, this causes a little bit of an issue because water itself has a vapor pressure, and that vapor pressure remains constant throughout the experiment, but it is dependent upon the temperature. And so here's an example of what we're taking potassium chlorate and some manganese dioxide, and we're generating oxygen gas, and that oxygen gas is being collected, but we're bubbling it through water, and so we have to take this pressure up here. There's some water vapor that contributes to that pressure, and so in order to figure out how much oxygen we have to subtract out the vapor pressure of the water. And usually you'll have a table for that. In these cases, you're going to be generally given how much pressure is from the water itself. So a sample of solid potassium chlorate was heated in a test tube and decomposed by the following reaction. So here we have the reaction we are just talking about, already balanced because we do have coefficients. The oxygen produced was collected by displacement of water at 22 degrees Celsius at a temperature of 754 torr. The volume of gas collected was 0.65 liters, and the vapor pressure of water is 22 degrees Celsius is 21 torr. So that's what I mentioned. You're going to have a table, or it'll be given to you because the vapor pressure of water at specific temperatures is constant. So it asks us to calculate the partial pressure of oxygen in the gas collected and the mass of potassium chlorate in the sample that was decomposed. So we need to first determine the partial pressure of oxygen in the gas collected, and then we're going to calculate the mass of the potassium chlorate in the original sample. The table here at the bottom of the page tells us what we know. So how are we going to get there? First, let's subtract out the vapor pressure of the water, and that tells us that the pressure of the oxygen is 733 torr. So the number of moles of oxygen, we use the ideal gas law to find the number of moles of oxygen. So the pressure of oxygen here, the volume of our container, our volume of oxygen collected, it was told in the previous slide. R is your constant. It told us what the temperature was 22 degrees Celsius. Because we want to use 0.08206 as our ideal gas constant, we do have to have a pressure in atmosphere. So we'll take 733 and divide it by 760. So here are our variables. We'll plug them in. So pressure, 0.964. We just calculated that. Our volume was given in the problem. There's our gas constant, and it was taken at 295 Kelvin or 22 degrees Celsius. So this is how many moles of oxygen that we produced. So we use the partial pressure to get there. How many moles of potassium chloride are required to produce this amount of oxygen? So we look back at the balanced equation. The ratio of oxygen to potassium chlorate is 2 moles of potassium chlorate will generate 3 moles of oxygen gas. And so here's what we got before. This is how many moles of oxygen we just calculated on the previous slide. Our ratio, according to our balanced equation, we'll need to put moles of oxygen on the bottom and multiply this out. We get that there were 1.73 times 10 to the negative 2 moles of potassium chlorate. We're going to use the molar mass to calculate. So this number goes down here. Use the molar mass. It's 122 2.6 grams per mole to figure out that we have 2.12 grams of potassium chlorate. So you can do a lot of things with partial pressures, and that was a very consuming problem. But you can, with chemistry, you can have one variable, and you can get to other variables very easily by knowing stoichiometry, by knowing things like Dalton's law of partial pressure, etc. Last slide. Consider a flask at STP containing equal masses of helium gas, excuse me, oxygen gas, and hydrogen gas. Which gas is the partial pressure going to be the greatest? So if we have the pressure of the total, and that's going to equal the pressure of each of the gases on their own. To find this, you remember we could take, in order to find pressure 1, we could take the pressure total times the mole fraction of the gas we have, or the mole issue. So we have equal masses of each of these things. So if we have equal masses, so let's say we have 100 grams of each. So if we have 100 grams of helium, we're going to divide that by 4 to get our moles. If we have 100 grams of oxygen, we're going to divide that by 32 to get our moles. And if we have 100 grams of hydrogen gas, which is diatomic, we're going to divide that by 2 to get our moles. So the whatever smallest number is on the denominator is going to indicate that that's the biggest number of moles, therefore the biggest mole fraction. So that means that the smallest molar mass is going to have the greatest pressure, because this is mole fraction, and this is basically going to be the number of moles of whatever we're talking about divided by the total number of moles. Okay? I hope that makes sense. That concludes lesson 5.5. We're going to talk about the kinetic molecular theory in the next lesson.